All right, let's go to the table chart problems. I'm naming it, I'm naming this model like that because the characteristic is that you're given a table of values. And so in this particular case, the table of values is um, the, I would call that the original function. It's not a rate function, it's the amount of coffee in the cup at the time for the specific values. I mentioned in the summary, but I want to say it here again, to always keep in mind the limitations of just having only specific sample values. So the limitations are the important limitations are that you cannot make any determinations about increasing or decreasing about in within any of the subintervals here. So in any subinterval between the given values, the function could go in and out, above, below, turn around, and do all kinds of things as long as it stays um, continuous and differentiable. But there are lots of ways that it could behave between the given points that makes it impossible to determine if they're going to be increasing or decreasing over any subinterval here. So the only thing that you're going to be able to apply is the mean value theorem by finding an average rate of change on any of the subintervals here, and then drawing the conclusion by the mean value theorem that there is a specific value that exists on the derivative of the function where the tangent line has the same slope, or the instant rate of change is the same as the average rate of change that you've computed over this integral. So here you can see B is exactly that type of question, and we'll go over this now in detail. Okay, let's start a new page for this one, and we'll determine as we go if we're probably supposed to use a calculator on this or not. Okay, so let's read it. Hot water is dripping through a coffee maker, filling a large cup with coffee. The amount of coffee in the cup at time between t equals 0 and 6 is given by a differentiable function c, where t is measured in minutes. Selected values of c of t measured in ounces are given in the table above. So we have minutes and ounces. Use the data in the table to approximate C prime of 3.5. So approximating the instant rate of change is done by computing the average rate of change on two values that are as close as you can get to the value, to the time of the approximation here. Okay, so 3.5 is right between 3 and 4. So you're going to take the average, to use the rise over run formula to take the average rate of change between these two values here, these 2 points. So C prime, I should say, of 3.5 is approximately the same as, let's start with the later function value here. So that's 12.8 minus 11.2 over 4 minus 3. And that is, what is this? 11, that's, looks like it's 1.6. Yeah. Yes. 1.6. So it's 1.6 over 4 minus 3 is 1. So it's 1.6. 1.6 ounces per minute. Okay, that's the average or approximate rate of change at t equals 3.5. Right? That's the answer for A. Okay, B. Is there a time between 2 and 4 at which C prime is equal to 2? Well, in order to answer that question, we have to find the average rate of change in this interval here. So we have to do this whole thing again here, but this time we're going to find the average rate of change. So let's call this average AVG on 2 and 4. I'm just going to notate it a little bit funkily here. So now we're going to use 4 and 2. So that's 12.8 minus 8.8 over 4 minus 2. And that actually is 2, right? This here is 4, and this is 2. So 4 over 2, and that equals 2. So this checks out because the average rate of change between 2 and 4 happens to be 2. So that does guarantee by the mean value theorem that there is a C prime of t at any point between 2 and 4, at some point between 2 and 4, where C prime is equal to 2. So by the mean value theorem, MVT, let's start out the other way. You can do it either way, you just have to say it so that it's most practical. So the average rate of change on the interval, on the closed interval, 2, 4 is equal to 2. Therefore, by the mean value theorem, there is a t in 2 to 4 where C prime of t is equal to the average, which is 2. Okay, that's complete answer here. Let's go to C. Use a midpoint sum with 3 subintervals of equal length indicated by the data in the table to approximate the value of 1/6 of the integral from 0 to 6 of C of t dt, and then explain the meaning of this expression in the context of the problem. So let's first do the problem. 1/6 of the integral from 0 to 6 of C of t dt is equal to the Riemann sum that consists of, let's keep this, so this here is the Riemann sum, right? This here, the integral has to be expressed as the Riemann sum, so we're going to keep the factor of 1/6 out front here. Let's see. So 3 intervals and midpoint. Okay, so this is always the case when we have, usually when we have the midpoint already given. So here we get 3 intervals from 0 to 2, from 2 to 4, and from 4 to 6. And we have the actual midpoint value already given, so we don't need to compute it. But that's often as practical as this. So from 0 to 2, the width is always 2, so we could factor this out again. But let's just say it like this. So it's 2 times 5.3 plus 2 times 11.2 plus 2 times 13.8, like so. Okay, so that's, we can factor the 2 out again from all of this. So we get 2, 6, that's 1/3 of 5.3 plus 11.2 plus 13.8. So let's see how much that is. This here is 12 plus 13 is 25. That's 25 plus 25.3. Is that right? 25 plus 5. So it's 1/3 of 25 plus 5.3. That's times 30.3, and that is 10.1. Okay, so what is this now? We have everything, right? We have the 1/6. Yes, we have everything. So 10.1, and this is going to be ounces. So now let's explain the meaning in the context of the problem. This means that the average amount of coffee in the cup between t equals 0 and 6 is 10.1 ounces. Average amount of coffee in the cup. I'm getting too low here. Okay, so I'm just going to do shorthand here. This is our answer for this. And we get to go to D. D is the amount of coffee in the cup in ounces is modeled by this function. Okay, the amount of coffee in the cup in ounces is modeled by this function B of t. Using this model, find the rate at which the amount of coffee in the cup is changing when t equals 5. So in this case, we're supposed to find B prime of t for 5. Let's see if we can do this by hand. B prime of t is 16 is going to be 0, then 16e to the negative, that's actually negative 16, right? So negative 16e to the negative 0.4 t. All right, that's the outside derivative of the second part. And then we have to use the chain rule to multiply by the inside derivative. So that is going to be times negative 0.4. All right. So negative times negative is positive. 4 times 16 is 64, but that has a decimal point. So that's going to be 6.4 e to the negative 0.4 t. All right. Now let's plug in 5 on this. So b prime of 5 then is 6.4 times e to the negative 2. And you can ship that as the answer like this, because we're not supposed to use calculator. All right, that's it. Let's double check our responses here. Make sure we got everything right. C prime of 3.5 is C of 4 minus C of 3 over 4 minus 3. That's this, 1.6 units, ounces per minute. Approximation is right, and the units are at the second point. C is differentiable. That means C is continuous on the closed interval. Therefore, and the closed interval 4 to 2 has an average value of, average rate of change is 2. Therefore, by the mean value theorem, there is at least one time t between 2 and 4 for which C prime of t is equal to 2. Okay, so the first point is earned by doing this computation here. We did that right here. And the second is conclusion using the mean value theorem. And we did that. Okay, now midpoint sum is given by 1/6 times 2 times C of 1, 2 times C of 3, plus 2 times C of 5. That computes like this, and the end result is 10.1 ounces. The interpretation is the average amount of coffee in the cup in ounces over the time interval from 0 to 6 minutes. And D, we found B prime of t, and that is the correct formula here, 6.4 e to the negative 0.4 t. So we found the formula, and then we computed this, and it's 6.4 times, how do we have it? Yeah, so this is close enough. You can put this into this form here, but that doesn't matter. But do make sure to have the units here, and this is again ounces per minute. All right. Yeah, they're not explicitly asking for the units here. That's always good practice to just put the units in. Okay, that's the next model.